Hey everyone, and welcome. Have you ever looked at a beautiful polar curve, like a cardioid or a rose, and just thought, how on earth would I find the slope of a tangent line to that? Well, you've come to the right place. Today, we're going to break down exactly how to find slopes and polar coordinates.
So, here's our game plan. We'll start by setting up the problem, then we'll uncover the crucial insight that unlocks this whole thing. After that, we'll get our hands dirty with a couple of examples, finding both horizontal and vertical tangents. And we'll finish up with a fantastic shortcut for tangents right at the pole. Okay, let's dive right in with our first section. We're stepping out of the familiar, comfortable world of Cartesian coordinates and into the slightly weird territory of polar slope. You know, we all get taught that slope is just rise over run, dy over dx. It's second nature. But a polar curve isn't built from x and y, it's all about a radius, r, and an angle theta. So the big question is, how do we find a Cartesian concept like slope in this totally different polar world? That's the puzzle we need to piece together. Well, the solution is actually super elegant. It's one of those aha moments that connects this new polar idea back to a tool you probably already have in your calculus toolkit. Here's the secret sauce. We're going to treat our single polar equation as a set of two parametric equations. We already know the conversion formulas, right? X equals r cos theta and y equals r sine theta. By thinking of theta as our parameter, we can basically build a bridge from this new polar world right back to the familiar land of parametric equations. And building this formula is totally logical, step by step. We start with those x and y definitions, then we bring in the chain rule for parametric curves, which tells us the slope is just the derivative of y with respect to theta, divided by the derivative of x with respect to theta. Now, since both x and y are products, we just have to use the product rule, put it all together, and boom.
And voila, here it is. Okay, I know this looks like a monster, but just remember where it came from. The top part, the numerator, that's just dy over d theta. And the bottom, the denominator, is dx over d theta. This is our master tool for pretty much any polar slope problem you'll face. All right, we've got the tool, let's put it to work. We're going to start by finding the horizontal tangents for one of the most famous polar curves out there, the cardioid, r equals 1 plus sine of theta. Okay, first things first, what is a horizontal tangent line? It's a line where the slope is 0. And for a fraction to be 0, what has to be true? The numerator, the top part, has to be 0. Simple as that. We don't even have to worry about the denominator right now. We just need to solve dy over d theta equals 0. So first, we need to figure out our y. Remember, y is just r times sine theta. In our case, that's 1 plus sine theta times sine theta. We apply the product rule, do a little simplifying, and we get this nice factored expression, cosine theta times the quantity 1 plus 2 sine theta. And just like that, the calculus part is over. Now we're just solving a trig equation. Since it's a product, the whole thing is 0 if either of the pieces is 0. So we've got two parts here. The first one, cosine theta equals 0. That's easy enough. That happens at pi over 2 and 3 pi over 2. For the second piece, 1 plus 2 sine theta equals 0, well, that just means sine theta has to be negative 1/2. And that happens at 7 pi over 6 and 11 pi over 6. But hold on a second. There's a trap here, and it's a really common one. Take a look at that solution, 3 pi over 2. If you were to take that angle and plug it into the denominator of our big slope formula, you'd find out it also comes out to 0. That gives us 0 over 0, which is an indeterminate form. What's happening here is that the cardioid is forming a sharp point, a cusp. The tangent there is actually vertical, which is a classic gotcha to watch out for. All right, so we've nailed horizontal tangents. Now let's flip the coin and look at vertical tangents, the places where the slope is undefined. And the beautiful thing here is that the logic is exactly the same, just flipped. For a horizontal tangent, the slope is 0, so the numerator is 0. For a vertical tangent, the slope is undefined, which means we're trying to divide by 0. So we just set the denominator, dx d theta, equal to 0. Let's try this out on a slightly different cardioid, r equals 1 plus cosine theta. Our goal is to set that denominator, dx by d theta, to 0. So we find the derivative of x, which is r times cosine theta, apply the product rule, factor it out, and we end up with negative sine theta times the quantity 1 plus 2 cosine theta. And again, it's the same drill. Set each factor to 0 and solve. Sine theta equals 0 gives us theta equals 0 and pi. Cosine theta equals negative 1/2 gives us 2 pi over 3 and 4 pi over 3.
And just like before, you'd want to double-check that the numerator isn't also 0 at these points to make sure you're not dealing with another one of those cusps.
Okay, after all that work with the product rule and solving equations, I've got a treat for you. A fantastic shortcut for a really common situation, finding the tangent line right at the origin, or what we call the pole.
And this is just a beautiful example of how math can simplify. Think about it. If the curve is at the pole, that means r is 0. Now look back at that monster formula we had. If you plug in r equals 0 everywhere, the whole thing just collapses down to sine theta over cosine theta. And what's that? It's just tangent of theta. Okay, watch how fast this is with the 4-petaled rows. R equals sine of 2 theta. Step 1. When does it hit the pole? We set r to 0. That happens when theta is 0 and pi over 2. Step 2. Find the slopes. The slope at theta equals 0 is just tan 0, which is 0, a horizontal tangent. The slope at theta equals pi over 2 is tan pi over 2, which is undefined, a vertical tangent. And boom, you're done. No product rule needed.
All right, let's wrap this up. What are the big things to remember? First, always use that parametric bridge to find the slope. From there, it's easy. For a horizontal tangent, set the numerator to 0. For a vertical tangent, set the denominator to 0. And if you're lucky enough to be at the pole where r is 0, the slope is just tan of theta.
And that leaves us with one final, very interesting question. We saw this happen at the cusp of the cardioid. When we get that indeterminate 0 over 0 form, what does that actually tell us about the curve? That's a deeper question, one that leads to concepts like L'Hopital's rule, and that's where things get really interesting.